Hi, I'm Michael DeLeo. I'm from the University of Johns Hopkins School of Engineering, and I'm presenting to you today my research on learning chess with language models and transformers. So some of the inspiration for this research is some of our fascinations with language models as few-shot learners and what they can learn in only a limited amount of data. Another point of inspiration for this research was also student-teacher networks and the idea of transferring knowledge learned of a particular deep learning network or another system into a smaller model potentially, or even a different model entirely, one that would not be able to normally ascertain this information itself through normal means. And the last thing that really inspired us was just huge advancements in the field of natural language processing for deep learning models, such as GPT-3, and in smaller cases, BERT. So some of the core concepts I'll be focusing on today is transfer learning, so which is the process of training a model on a different data set, given that the new data set is similar to the original model's data set. Natural language processing in that NLP models are few-shot learners, and student-teacher networks, which is the process of training a smaller or different version of a model, which is our student, through predictions of the larger model, which is the teacher. So our research question really is, can a language model improve, speed up, or learn from a reinforcement learning model? And so our first approach for taking a crack at this was using a small toy game as an example. And in this case, we used Nim as our proof of concept environment. And for those of you who might not know, Nim is just a very simple game of you have n piles of m items. In this case, it's just some arbitrary item. And here we have 3 piles denoted as piles A, B, and C with 10 items each. So the game works by 2 players alternate taking some amount of items from 1 pile only. And the person to take last wins the game. And so there are 2 agents that are particularly very good at this game. One of them is called the Guru player, which uses a set of XOR operations to determine the best stack to pull from, and it tries to maintain an even distribution of items between all the piles. And then the second agent is a Q-learner algorithm, which we used in just a simple way of random exploration and simple rewards and losses for the states that it reached. And so an example of how we might encode this set of states into text is seen here, where you have the left-hand portion being the state space of the game, where you have 3 piles. So it's B3, so that's the ID and the amount in that pile. And then you have the other 2 piles, C9 and A8, with the slashes delimiting the, designating that these are the states. And so really when we came up with this format, we really had to think about what is the grammar of this language to this model, and how do we separate that our action space is really different from our state space. And the last part about this sequence here is we also included an agent token. In this case, the agent is Guru, so it's just a G to denote that with this current state in this model chose to make this move, which is taking 2 items from pile B. So bringing this into our student-teacher network, we chose the Guru and the Q-learner, and as a baseline, we chose a random agent so we could ascertain whether or not this actually learned anything. And we set these up in a tournament style so that each model would play a copy of itself and every other model in the roster. And we had them all play 200 games each, recorded those, and ran through 10 iterations of noise generation. And so by noise generation, I mean, for the first iteration, you would have a 10% chance of randomness. So for 10% chance of randomness, Guru has a 1 out of 10 chance of having their action replaced by randomness instead. And when that randomness is replaced, you would still keep that agent tag to show that, oh no, here's some noise. Can the model actually see through this? And just a refresher on BERT, in case anyone is curious, BERT stands for bidirectional encoders from representations of transformers. It's a very interesting model. There's a lot of interest in it in the NLP space. It's so popular, they've even dubbed a subcategory of a subcategory called BERTology because people love it so much. And BERT learns from bidirectional context in text corpuses. So when we really think about our sequence from before, when BERT analyzes the agent tag, it's really also analyzing what's the context in this sentence for the state space as well as the action for what makes sense here. And so for Nim, we plotted some of our results. So like I mentioned before, we have our randomness from 0 to 100%, or 100%, or 90%, excuse me, where 9 out of 10 would be 9 out of 10 chance of randomness being injected into the game. And you can see for different models, we have the Q-learner, random, Guru, and then another novel type we experimented with, which was win in local states instead of the agent. And so we found that something really interesting happened. Before 30% randomness, the BERT model performed less effectively than the other models in the tournament. But after and at 30% randomness and higher, it actually seemed to be more proficient. And so I guess I should explain more about what this means. And it's because at 30% randomness, these models have a 3 out of 10 chance of random being injected and then that being played as the move. BERT is on the same playing field because it's also learning from that. So it's being told to play as Q-learner here, but that Q-learner model that it's learning from made 30% mistakes. So it's its own choice whether or not to play those moves. That Q-learner also played itself for this game. And so since we showed with that, that the BERT model can learn how to play a toy game, we approached chess as a larger state space. And the state space for chess for the number of moves is like 10 to the 50th power. So we wanted to approach a different thing first. So some of the agents in chess that are considered to be state-of-the-art today, as opposed to Nim. The first one is AlphaZero, which is a model developed by DeepMind. It's a Google-owned subsidiary. So this model is proprietary. It's a little difficult to get your hands on. We weren't able to. And it was trained on 2.8 billion board positions. It's a deep reinforcement learning model. And each training step was 4,096 board states. And it took 9 hours to train for them. And so AlphaZero uses a very general cost function and a Monte Carlo tree search algorithm to search the number of positions and find the right move. And it's technically considered the #1 chess algorithm. The other chess agent we're considering was Stockfish. And there's 2 variants of Stockfish out there. There's one where they use a heuristic to evaluate your board position to determine who's winning. And there's another version, the NNUE, which uses a small neural network to evaluate your board position. So in this case, it evaluates it as +0.4, so +0.4 in white's favor. And so essentially, Stockfish works by heuristically searching the state space with an alpha beta search and tree pruning to assess the best moves. And so we ended up choosing Stockfish because of some of these reasons mentioned, that AlphaZero is not publicly available to us. And Stockfish actually has some really nice features of it having its own chess engine, and the evaluation metrics are very useful as well. And so we take that same concept mentioned earlier of the student-teacher network paradigm, and we insert Stockfish into it rather than the other agents. And so we essentially set up Stockfish to act as a high-level grandmaster chess player, played against itself for, as we recorded it, 30,000 games. And we recorded the first 6 moves of each game for the model to ascertain an encyclopedic set of opening knowledge of chess itself. And so some of the sequences are actually shown here. So they're really similar to the Nim sequences. Here you have a Ben sequence, which is essentially a representation of how do you encode, or how do you get to this board state, this board position from the starting board position. And some interesting things that are encoded here are actually the next player to play. So in this case, it would be white. In this case, it's black. And then following that, we have a separator token. And then afterwards, we have algebraic notation for the next move taken. And we decided to keep things a little simpler. So we didn't have knight takes or knight x e5. We had d7 b5, which excludes some of that information, but it keeps our notation simpler for the fact that we just want the model to be able to say, I want to move from this coordinate to this coordinate. So some of the training specs for the model we use, it trained for 104 epochs with a batch size of 382 on an RTX 86000. And the data set had 30,000 games in it. And the tokenizer had a size of 16,000. And we mentioned that because we had to pre-train the model, actually, because the original encodings were not accurate or set up enough for this application. And we had 6 hidden layers for the model. So for the software implementation, this was our loss curve. And we used the Hugging Face Transformers library to assist with the implementation as well as PyTorch and CUDA 11.4. And for our results for chess, they were actually rather striking. So here is actually a game of the BERT model playing Stockfish, where BERT is black. And I'll stop it at some point because it's not terrible in the beginning. It makes some questionable moves, but as it goes on later in the game, it seems to completely disregard the safety of its king and lose 3 or 4 pieces. And at that point, it's completely lost. But there is a position coming up pretty soon where it does actually put the king in check. And if you had seen before, it actually also put, it castled the king. And this is where it just completely loses. And so, yeah, so we really think that some of these inaccuracies were caused by the model's depth into the game. So we really just wanted to start out with chess. As I mentioned before, chess has a very, very large state space. The number of possible positions or possible board states is 10 to the 50th power. So this is really our introduction to chess here. And so, as I mentioned also before, the model had a difficult time beating Stockfish. We didn't actually show that it could win a game. We never showed it how to win a game. But instead, what we show here is actually how long it can go up against a grandmaster level chess player, as in Stockfish at an ELO level of 3,200. And I can tell you for sure, this one, it lasted for 30 games, or excuse me, 30 moves on average. And I can tell you that if I played a grandmaster, I'd probably get checkmated in about 5 moves. So it's doing rather well. So one of the other things that we wanted to measure was the model's accuracy, because since the model's action space was not well defined as in reinforcement learning models might be, we wanted to give it the freedom, the creative freedom to say whatever it wants to. It could say Facebook and we'd say, okay, that's great. That's an illegal move. You can't say Facebook. You have to say knight to d7 or this or that. And so that's what we say. But when we say accuracy, we say, is this a legal move or not? So we're really testing BERT's understanding of chess itself, given this state space and the next move it wants to make. So we're really testing, can it grammatically understand what this board position really is? And so using that kind of evaluation metric of what's illegal or not, we showed that over the course of a game, we can see that for the first 6 moves, it's very good because it has an encyclopedic understanding of openings. As it goes on, it seems to plateau at about 70% accuracy throughout the game. And when we say 70%, that's 7 out of 10. And when the model gets it wrong, we go through the next top K answers that the model has to give us until we get the correct answer. And so when I talk about the action space for the model, something that we have to mention is the statistical coin toss or receiver operator curves, in that are we just getting lucky? Is this better than random? And so for how we've defined the problem of the action space being column row, I would say that we are not, in fact, getting lucky, that the model does have some kind of understanding of this board state. Because if not, I mean, you could say right now, B4, C5, that's just wrong. But if you were to have a random generator just come up with random moves, the accuracy would be incredibly small. Yeah, and so we think this process worked because language models are few-shot learners. They can gain quite a great deal of knowledge from sparse data sets. And BERT is most probably finding correlations between similar move sets and the game position. And that's why, for one reason why, in the late stages of the game, it can sometimes struggle to play against the opponent. So this is impactful because there's some really interesting applications or implications that occur because of this idea or this notion of generally taking a complex system where an existing state-of-the-art model has already been trained and reapplying that through another model's understanding. And one of those could be taking the logs of a deep learning model that you've been training for a year, and oh no, the power went out and you didn't save it, but you have the logs. You can recreate that, potentially, some of its understandings through this method of recreation just from a very low cost method. And there's also some other unique implications. So when we tested this model, we really only asked it for the action, but there's also the situation of, hey, given this move and what I know about this board, say I only know half of the board state. So there's a version of chess where you have only knowledge of whatever your pieces can see. And so in that case, you can only fill in certain portions of the fence state. And you could say, I want to move here. What's the likelihood that there is a piece here, given your understanding of this player, for example? So there's really interesting nuances that can come about from that. And so this model is also hosted. Anyone can check it out. We dubbed it, cute name, BERT Harmon for the Netflix series Beth Harmon. And it's on Hugging Face. You can check it out yourself and try it out. And the code is also hosted up on that link on my GitHub repository under NLP Chess. And I can probably go through a quick demo, I guess, but only if people really want to. And any questions?